Here's a look at a key for the midterm. So this first one is just constant acceleration. You're throwing the ball up at 5.1 meters per second. The acceleration acts down. So you have to watch your signs on this. Just apply a constant acceleration equation. You'll get that velocity right there. Okay, the second one, I had a bust in. I had some problems with the draft of the test, and I've got the acceleration up, but I want to know the velocity when the ball is down below. That led to a sign error, so I just omitted that problem there. I just gave everybody credit for it, so I didn't grade it. I just gave everybody credit for it. It should have been solved with ADS as VDV. All right, the next one here, what we have is a trajectory problem. You need to vectorize the velocity into x and y components. Apply this constant acceleration equation for the y direction and see when the position would be 0, when it would hit the ground basically, and solve for the time. And that has two solutions. 0 is when it starts, 3.96 seconds is when it hits the ground. Then apply that same equation but in the x direction and plug in the time, multiply it by the velocity, and you get the distance in the x direction. So the important thing on this is to treat that like a vector and to break it up into x and y components. All right, the next one here, we have a collar rotating on a circular path here on a track. We want to find the total acceleration. You got the velocity, so take v squared over r. You'll get the normal component of acceleration. Okay, you're also given the tangential component of acceleration in the problem statement. So to find the total acceleration, you just take the square root of sum of the squares. Now, had you gone with a polar approach, the inputs would have been like this. A number of you tried a polar approach. The important thing there is because you're on a circular path, both r dot and r dot dot are 0. Then you just plug all those into the acceleration equation for polar. But I think this is the simpler approach right there. Okay, the next one was a spiral problem. You're given the radius, 3,000 minus 200t. So that's 1,200. Take a time derivative, you get r dot is negative 200, r dot dot, which is the acceleration of the radius, would be 0. You're given that the angle of the satellite is 0.24t squared, so take a time derivative, you get the angular speed, 0.48t. Take another time derivative, you get theta dot dot at 0.48. Then you just plug everything into the acceleration equation, get this acceleration vector, take the square root of sum of the squares, and you get the magnitude of acceleration. All right, the next one here, we get a free body diagram. So I just went ahead and showed the normal forces and calculated the frictions, 4 and 2.59. Then to find the tension, you go sum of F as MA. So we've got the static stuff here on the left, the 17 newtons to the left, I'm calling left positive, minus the 2 frictions, and that equals the mass times the acceleration. The mass is the total mass, the sum of the 2 masses. Given that, you can find the acceleration. Now to find the tension there, you need to cut one of the blocks out so that you cut through the cable and can find the tension in the cable. You can't find the tension by treating the system as both blocks, because then the tension is internal, and it's internal force that you would not be part of the equation. The other thing on this is it seemed on a lot of people's solutions, they weren't using the method that I covered in class, which is static stuff on the left for forces, masses, and accelerations on the right. So I would encourage you to kind of use that method as we go through the rest of the class. We'll come back and do some things like this. And that's the most consistent way, that I know to solve these. Now, of course, you can solve them in any valid way you like, but if you had problems on this, you might kind of go back to that approach and also use this approach in the class. It's how I'm teaching it, and I think it's an effective way to solve these problems. So what I've got here are free body diagrams for block A and B. You do F, which for A would be 17 to the left, the friction to the right, and the tension to the right. So it looks like I'm calling to the left positive here. And then you set that equal to MA and solve for the tension 10.32. You can do the same thing for B, tension to the left, friction to the right. So tension minus 4 is the mass of B times the acceleration. You get the same tension. Another thing I'll mention is if you just sum forces on this without breaking out free body diagrams of A and B, you end up getting a sum of forces of 10.41, I think it was, which is quite close to this tension, but that's coincidence. I checked that, the numbers on that, and ran something there to check it, and the 10.41, even though it's quite close to 10.32, it's simple coincidence that those two things were close. You really do need to do an F equals MA for one block or the other to solve for this tension. All right, the last one here, this one uses the English system, and we want to get comfortable with that. You wanted to realize that pounds are weight, and if you take the pounds over gravity, 32.2 feet per second squared, you get slugs, which are the English system of mass, also called the imperial system. Okay, you want to go sum of Fy, set that equal to 0, and that'll get you the force of the road, 2857 pounds. Multiply that by the coefficient of friction, you get the frictional force, 1200 pounds. Then you can sum F equals MA. You get the 1200 friction minus the component of the wind going the other direction is equal to the mass times A. So A is 11.65, and that equals V squared over R. So that'll get you the velocity at 93.5 feet per second. So this was in the imperial system. It is worth learning this because we still use the imperial system here a lot in this country. It's used in industry a fair amount, so it's something to be comfortable with.